So this is the EL power circuit working space. So this is essentially a battery starting system and charging system test. So you can see you can populate a pile of different information depending if you meet requirements for those measurements. And this is what it looks like after you've run the test. So you can see it generates a bunch of different information based on the oscilloscope measurements. And this is what I captured on the oscilloscope. You can see it's about a minute long. The whole process includes switching the loads on and off, running it at a higher RPM, and then also switching the loads on and off. But it'll show you your charging voltages. It'll show you your averages. It'll show you the ripple. This will give you a starting quality diagram and then an oscilloscope window of your starting event averaged. And then these options in the upper left-hand corner up here will change the view of this window so you can see specific things like the solenoid contacts closing, which you can kind of see here, but it'll zoom right up on it so you can see exactly what's going on there in case you want it a little closer for analysis. This also prints out here in a nice black and white layout that'll give you your graphs and then this breakdown here as well. So you can attach that to a customer invoice or present that to a customer. So this is the cylinder balance working space. This test can be used to identify a cylinder-specific misfire. This analysis can be performed live on a vehicle or on a recorded file as long as you meet the requirements of the analysis. And that's what that looks like, all said and done. So you can see all we have on the oscilloscope window is a crank sensor waveform that's really shrunk down. You can't really see the signal, but trust me, it's a crank sensor waveform. And then this is your trigger channel or your IFC. And this is a number one sync over here. And with just these two traces, we're able to generate a report based on crankshaft speed and your ignition timing to determine your misfires. And you can see here this thing's running great. Through the snap throttle, it runs great. And you can see here, actually, I unplug an injector, and you can see one of the cylinders drops out. And in this case, it's cylinder 5. These bar graphs on the right side represent the averages over time. There's an option up here in the toolbar to change how much time it's looking at for the bar graphs. But if you have a dead miss, it'll definitely pick it up really quickly and really accurately. I did a bunch of playing around with this to find out how inaccurate I can make it, and it's pretty hard to fool. So as long as you set everything up right, this is awesome for, say, early OBD2 vehicles that don't have misfire monitors, or if you think a misfire monitor might be lying to you, this is a quick, easy test to prove that the cylinder you think is misfiring is actually misfiring. And this does this based on the calculation of the acceleration of each power event as it goes through the firing order. Then you can see it'll graph the ignition timing as well as this orange trace, and then RPMs is the gray trace. So, and again, there's other tabs that it'll show you the ignition timing in a 3D map. And actually the next page shows you the crankshaft reluctor gear pattern, which is really nice as well. And this automatically generates this based on this file. So it counts the reluctor teeth for you. If you thought you had, say, a damaged reluctor tooth, you would actually see that here. And it would show up consistently, so it would show this inaccurately consistently. So this is probably one of my favorite tests to do with this. And again, it's really quick and easy to do as long as you can get to the crankshaft signal pretty easily and grab a sync on any spark plug. The secondary voltage working space is another one that I use regularly. You don't need it, but the amount of data that it captures, collects, and displays to you really makes analysis super straightforward, super easy. But you have to have the proper procedures and setup. And I'm going to show you that. Here is the capture. So this is a V8. I have the purple lead is just a pickup on the coil signal or the coil secondary wire. So this is just the wire going from the coil to the distributor cap. And then my trigger is set on number 1 cylinder. So this is all it is. It's 45 seconds of this engine running plus a snap throttle or 2. So this is what it looks like after the analysis is run. And you can see it displays the waveforms of all the cylinders. Here is my frame by frame. So I can cycle through this. I could play the whole file. I can double click here and put in the frame I want to see and then hit enter and it'll take me right to the frame I want to see. These graphs on the right side are, you can see that these numbers across the bottom are your frame numbers. So what's cool about that is I can see here is my RPM in gray on each one of these. And you can see when I do the snap throttle, something happens. You can see my firing voltage and my spark burn voltage line. One of the cylinders sticks out more than the other. And I want to make clear what these are. So the firing voltage is this peak voltage here. The spark firing voltage is this voltage here, where it leaves the initial firing voltage. The spark burn voltage line is actually the length of this line in milliseconds. So we can see that something happens right around frame 60 as we open the throttle and raise the RPMs. You can see that the spark firing voltage goes high on cylinder 1. You can see the burn voltage line goes way low on cylinder 1. So if we jump to frame, I think it was 61 actually. Yeah, 61, where the misfire happens, we can see the misfire. And then we could use our secondary analysis skills to decide what that means. And I'm sure all of you guys here probably all know what that means. But if you don't, then that's a typical indication of a misfire happening outside of the cylinder. You can see that the voltage goes really high, and the burn time is about half of the normal burn time. So I'm looking for a secondary ignition misfire leak. So I'm expecting that voltage is going down the side of a spark plug, or leaking out at a bad spot in a wire or something like that. But you could plainly see this without even seeing the actual waveform right here in this graph. So it's really easy to pick out that I definitely have a problem here. And I'm going to jump right to that frame and look at this. So we go back here, you can see that's a 45-second capture, about less than a minute to run this analysis. We can look over here and go, I'm going to jump to frame 61 and see what's going on. Jump to frame 61, see this, and I know what's going on with the engine, with the ignition system, and why the misfire is happening in 5 or 10 minutes. So this doesn't take a bunch of time, and it's a simple, easy, fast test. The most important part is the procedure to set it all up. So for the in-cylinder working space, there is no working space. You have to go into the analysis and open up the pressure inside cylinder tab. And when you set up your probes, you don't want to set them up in PSI. This is a metric-based system. This was designed in a European country, which means they're going to use metric. All the math is based off metric numbers. So the math isn't correct if you use PSI. But if you use BAR or barometric, it will show up. So I have everything set up for bar, and that's what I would use when you set up your pressure transducers. So again, with the in-cylinder, this is just an in-cylinder pressure transducer. You see I've got a snap throttle event here and a snap throttle event here. So then once we run the analysis, it will show us each event with a frame by frame, and you can add a crank sensor signal and a trigger for a ignition sync, and it'll give you a ton more data. So the data is, you have cylinder air mass that it'll calculate. You have valve timing. It'll show you your exhaust valve closing and your intake valve opening under valve timing. In a really neat timing chart. The intake manifold pressure calculation, and then your exhaust pressure calculation. So the exhaust pressure is really nice if you're suspecting a plugged exhaust. You could do this test, look at this tab, and then decide if you're creating too much pressure in the exhaust. Then it also maps your ignition timing in a 3D map, uh, which I don't think many people are going to use. If you're doing reverse engineering or custom tuning, it would be handy, but otherwise, it's also kind of nice for just distributor setups. I've done a few where I just want to make sure the distributor curve is doing what I expect it to do, and this does a really nice job of that. So this is the cylinder comparison workspace. So this is where you would run a relative compression test, or say you're using an intake delta sensor, or using a delta sensor on the exhaust, you would run it here. To be honest with you, I'm not really a fan of this, just because I find it, I've done it for so many years manually just by looking at the waveform, that I'd rather use the ruler and the cylinder overlays than set this up and run it. And the reason for that is, sometimes you're going to run into a weird set of circumstances. It's not going to make it run very well. But then typically you have an obvious problem. So this test is nice when you're trying to pick out very little problems, like this intake valve leak here on cylinder number 3. This engine actually had a lot of different problems. The guy cooked it and drove it 20 miles with no coolant in it. So, but it was a good case study anyway. But you can see how this generates this. It lines it all up for you, because clearly we're on cylinder 1 here, and it moves everything around as long as you set it all up right.